Welcome everybody. Thank you for being here. Thank you for attending this apparently very interesting session and very interesting lightning talk session about machine learning. My name is Matteo Fontana. I am a postdoc at Politecnico di Milano, who is one of the organizers of this conference. I will be the chair of this session. Let me start by saying a very big thank you to the organizers, to all the organizers. This thing has been very hard to organize. We also had the coronavirus in the middle, so I mean it has been tough. It has been very, very tough. So thank you for the absolutely magnificent job. This conference is very cool. It's very nice and very, very interesting. And I think this experience of online conferences could be a trailblazer if you want, so something that should be done again in the future. And special thanks to, hi Stefan, special thanks to Emanuela Furfaro, who is the responsible, who is going to be the person who is helping me in handling all the speakers and all the nuts and bolts of Hopin. And thank you to Martin, who will be my aide for question time. So let me remind you, and let's remind the audience about the format of these lightning talks. Each speaker will have 5 minutes. We will have five speakers, and the questions will be in a dedicated Q&A session afterwards. So if you have a question for a given speaker, just put it in the chat, and someone will take track of it, and then we will ask the speaker to answer it during the question time. So we can probably start with our first speaker, who is Florian Privé from Aarhus University. He's a postdoc at Aarhus University. So are you in, I guess? Perfect.
Yeah,
Florian, please start to share your slides, and so we can start. Okay, perfect.
You see that?
Yeah.
Yeah. Hello everyone. Today I talk about my package bigstatsr, and particularly about function to fit penalized regressions very fast. First, let me talk about the format that package bigstatsr is using. For example, if you have a standard R matrix that would take 100 GB of RAM to be stored, let's say that you have only 64 GB of RAM on your computer, then it won't fit, right? But it would fit on the disk. So in bigstatsr, I use a matrix format on disk and access this data from disk using memory mapping. And let me also remind you about penalized regression. So here, in the case of penalized linear regression, you want to find the betas that minimize this penalized loss function. So first, there is the loss function of the linear regression, and then the penalty term. The penalty term is composed of a combination with the norm 1 and the norm 2. And when you have only the norm 1, then this is the lasso penalty. And when you have a combination of both, then this is the elastic net penalty. So basically, you have two hyperparameters in this model. And what is the science and implementation behind the penalized regression framework of bigstatsr? First, it is coded in C++ to be as fast as possible. It uses strong rules that allow us to discard variables that will never enter the model, so that you can fit the model on only a subset of the data. It also uses a early stopping criterion to avoid fitting costly models. And finally, my implementation directly does some kind of cross-validation internally, which can be performed in parallel because the data is stored on disk, which makes parallelization easy and efficient. Now let me present you two applications from my work. I work as a postdoc in predictive human genetics. I use very large matrices of genetic variants to try to predict diseases and other traits such as height. Here, in this example, I was able to fit a logistic regression with lasso penalty on a matrix of 15,000 individuals and 280,000 genetic variants of the variables in only a few minutes with this implementation. And in this other example, I used an even larger dataset with 350,000 individuals and 560,000 variants, which would take 1.4 terabytes of RAM if stored as a standard R matrix. And I was able to fit a linear regression with a lasso penalty in less than 1 day using my implementation on this huge dataset. So what you have to remember out of this talk is that with R package bigstatsr, you are now able to fit penalized regression on hundreds of gigabytes of data. And if your data is in matrix format and want to learn more about this package, you can look at this first publication in bioinformatics. And the second publication here described the efficient implementation of penalized regression that is available in this package. And with an application to genetic risk prediction, because we have very large data sets in human genetic, as I've shown you. And finally, please open an issue or email me if you want to contribute to this package, or if you want to build a new package on top of this package for your own applications. And please go check the package website, because there are more features than just fitting penalized regression in this package. Many more features, so go to the package website and also check the vignette on how to fit penalized regression with this package. And you can reach out to me on GitHub or Twitter. Thank you for your attention.
So thank you, Florian, for the very, very nice and interesting presentation. We already have some questions, and so very nice. I also have some questions too for you, so thank you. I think we can move on with our second speaker, with Krystian Igras, who is a data scientist and software engineer at Epsilon. Florian, okay, perfect. Hi. Hello. I hope I pronounced your name and surname correctly.
Actually, I haven't heard because there was connection problem, but I hope so.
Okay, perfect. So fantastic. So please start sharing your slides and start your presentation. Thank you.
Mm-hmm. Okay. All right. Can you see it?
Yeah.
Okay. Hi, everyone. I'm very glad to be here. I'm Krystian Igras. I'm data scientist and software engineer at Epsilon Data Science Company from Poland. I'm the author of xspliner package that was a part of my master's thesis written in 2019 under supervision of Professor Przemysław Biecek from University of Warsaw. I will talk how xspliner can be used to create explainable machine learning models that can be used to make deliberate business decisions. This is a short talk, so feel free to send me questions afterwards. So why explaining machine learning models? Throughout the history of ML, we've had multiple situations in which the application of machine learning resulted in unexpected and dangerous outcomes. One popular example is recruiting tool from Amazon in 2018 that was discriminatory against women in decision-making process. So we want to explain or build explainable models in order to avoid such situations, gain trust in our models, and make sure we know exactly how the model supports our decisions. In the ML world, we may observe the following trend in terms of complexity, accuracy, and interpretability. Typically, the more complex model is, the more accurate it is, but also much harder to be interpreted. So the goal of my master's thesis was to find out whether it's possible to extract some properties of complex machine learning models and try to use them to train the simpler ones. As a result of this idea, we worked out the following approach. We take black box model, we extract marginal model responses for each variable. Such responses are usually irregular, so we approximate them with splines. Splines approximations are used to transform the variables that are passed to train generalized linear model. Let me explain now the details of such approach. So as a marginal response, the most common are Friedman's partial dependence plots. I created a short video to show how PDPs are constructed. I plotted here predictions of a simple black box model trained on two variables, x and z, and predictions from training dataset as red dots. Freezing all the variables except one and iterating over its range, we can see how the predictions behave for the selected observation variable. As a result, we create so-called ICE curves, in this case for x variable, and then taking an average of all the ICE curves, we create just the PDP function. Now a little bit of math and motivation for such approach. When you create GLM model and use some functions to transform its variables, let's say GI in this slide, the PDP for resulting model are linear transformation of the corresponding GI function. As a result, the choice of functions that should be used to transform GLM variables is obvious. Our GI function should be PDP for corresponding variable of original model. Nevertheless, in our approach, we decided to approximate PDPs before we use them as transformation functions. The reason for more smooth. More to that, we found out this gives good properties to final GLM model in terms of predictions accuracy. The approach I presented a second ago was implemented in an xspliner package. On its GitHub page, you may find many examples and articles how to use it. In the GitHub itself, don't bother to ask me questions or complain if you miss any features. I'll respond for sure. For the final part, I want to present a simple credit scoring use case, how to use xspliner model to make deliberate decision whether a client should be granted credit or not. So let's start. In the model tab, you can find basic model statistics and model decision threshold in terms of log odds and probability. Based on the shape of GLM model, we can easily see how each variable contributed to the final score. More to that, thanks to xspliner approach, we can force the approximation to be monotonic, what can be required property from the final model, but couldn't be achieved by using most ML models. Yeah, in the client tab, we become creditor and start making the decision whether the person that asked for a credit should receive it or not. We simply fill a form with client-specific values, such as monthly income or number of dependents. After 2 seconds, we receive the model prediction. Unfortunately, we will not grant the credit in this case, but we can easily see where the client was placed in the model and which variables prejudged that.
You have one more.
And this is not all. We can prepare detailed report to the client to inform how exactly the data related to the client contributed to the final score. We also see if the local trend was positive or negative. And we can prepare the top recommendations, how the client could improve the score. This is quite straightforward because we know the transformation functions. So that's all. Thank you so much and see you in the Q&A session.
So thank you, Krystian, for the very interesting presentation. And I can see there are already some questions for you, so very nice. So let's welcome our third speaker, who is Mustafa Cavus. I hope the surname was tough to pronounce. Please, Mustafa, come to the. Sorry.
Hi, Matteo.
Hi.
Hi, Matteo.
So please start sharing your slides so we can start. Your presentation, or you can start your presentation.
Yeah. Can you see my presentation now?
Yeah, we can.
Thank you.
5 minutes.
Okay, thank you. Hi, everybody. I will talk about my packages doex and introduce its tools for ANOVA. Let me introduce myself. I am a PhD student in the Department of Applied Statistics at Eskişehir Technical University in Turkey. And I have been using R since the lectures of Marek Kagalewski in 2011, thanks to him. I'm also founder of Eskişehir R user group, and my research interest focused on deriving powerful statistical tests for ANOVA under non-normality and implement them in my package. As you know, one way ANOVA is basic statistical analysis to determine whether there is a difference between several population means. For ANOVA, Fisher F-test is often used for testing this hypothesis, but F-test has some strict assumptions. These are variance, homogeneity, and normality. However, when one of these assumptions are violated, the power of f-test is decreasing dramatically. Of course, there are some packages in Quran consist alternative methods for ANOVA, but most of them focused on the violation of variance homogeneity. So we decided to create a package, it's doex. It is focused on the violation of normality assumption as well as the violation of variance homogeneity assumptions for ANOVA. And it consists 3 groups of tests. First group is for violation of variance homogeneity. Second group for violation of normality assumptions. Also violation of variance homogeneity. And this group subset is divided 2 subsets. In the first group, under the violation of normality assumption caused by just outliers. And the second one is non-normality following another parametric distribution, and it is the focused part of our study. And I want to talk about the test in doex. There are 15 heteroscedastic ANOVA tests, 2 tests for non-normality caused by outliers. These are MGF and RGF. They are proposed by us, and you can see the details of these tests in our paper in the footnotes. And the last group is ANOVA test for 2-parameter exponential distributions. These tests are based on generalized p-value, parametric bootstrap, and fiducial approach methods. And also we deal with a problem by using doex in the product reliability. In here, data consists the lifetimes of the components which are produced by different suppliers in a local factory, and we want to test the difference between the mean lifetimes of these components by produced different suppliers, and we need to test these null hypotheses, and the data is distributed right-sticked as you've seen on the histogram, and we sure that it is non-normal by using Shapiro-Wilk normality test. You cannot see, but its p-value is near to 0. So we decide to use the methods derived for 2-parameter exponential distribution, and we choose the parametric bootstrap test because it is very powerful in small samples. So according to the results of this test, there is no evidence to reject the null hypothesis at the significance level 0.05. So we conclude that there is no difference between the mean lifetimes of the components produced by different suppliers. And finally, we have some plans on our package. We want to expand it with adding new tests for different distribution except 2-parameter exponential distribution, such as log normal, inverse normal, and so on. And also we want to add some tests for post-hoc comparisons under the violation of normality assumptions. And also we want to add some tests for higher way design except one-way design. And I am done. Thanks for your attention.
Well, thank you, Mustafa, for the very interesting presentation. And I would like to underline that Mustafa won a travel grant to come to Milan.
Yeah.
But yeah, unfortunately, let's say it wasn't needed. So yeah.
Also, I want to thanks to e-Rum2020 organizing committee for accepting my application for travel grants. I hope to be in there, but this organizing online is so well organized. Thank you.
Thank you, Mustafa. So let's move to our 4th speaker, who is Professor Øystein Sørensen, who is an associate professor at the University of Oslo.
Hello, good morning.
Hi, Øystein. So please share your presentation, and so we can start. Oh, sorry.
Just one moment, please.
Yeah.
Can you see my presentation now?
Yeah, we can. Perfect.
Yes. Then I'll turn off my camera, and then I'm ready to go.
Okay.
Great.
5 minutes.
Yes. So ranks and preferences is something that's common in a lot of applications. For example, you can have data that consists of information on what products a user, or what ads a user clicked on, or what product a user bought when the user had a choice between 2 or more alternatives. And if you're a company selling products or selling ads, this might be useful in order to determine some actions, like what is the next product or the next ad that should be recommended to the customer. And this is well known, and the field of recommender systems is huge. But one thing we saw that is missing a little bit is the ability to create probabilistic recommendations. And sometimes that could be very useful, because if you quantify the uncertainty about a user's predicted preferences, then you get a better decision-making tool. For example, if you're uncertain about what the user likes, then maybe you shouldn't send the user anything at all to avoid spamming. And maybe it's better to opt for a recommendation that has a slightly lower expected value if it also has a lower variance, so you're more certain about it, if it comes to a product recommendation, for example. So it's important in determining business cases. And one model from statistics that can be used to model this is the Mallows rank model, which considers row, which is a latent ranking for every customer segment, and the user's ranking we call R, which is the observed data. So you have a sampling model, which is based on the distance between the mean in the segment that the customer belongs and the user's data. And in the BayesMallows model, which is implemented in this package, we extend this Mallows model with clustering of users. We can have preferences that are in the form of pairwise comparisons, choices. We can have inconsistent data, and we can also predict preferences. And it's all implemented in a package called BayesMallows. And one example data set in this package, just to illustrate how it works, is 60 users were asked for their preferences in 25 random sets of beaches. So they were shown 2 and 2 beaches, and they were asked to choose which one is the nicest. Where would you rather go? So we had 15 beaches, and we had 25 preferences between the pairs. So the data were sparse because you can have at least many hundred different pairs of beaches. So we don't know the preferences of all the beaches from each users. And in order to fit this with the Mallows model, we can run the compute Mallows function, and we can provide the beach preference data. And we can also set the number of Markov chain Monte Carlo iterations, and we get the little printout as is written here. And based on this, we can, for example, do MC-MC diagnostics. We can see how each user's preferences develop with the number of iterations. So here we see different beaches, and we see sort of the estimate of the latent ranking within a given customer segment for each of those beaches to assess the diagnostics of the Markov chain Monte Carlo. We can also plot posterior distributions. For example, this alpha parameter in the Mallows model, which is like a variance just in the permutation space. And we can use the plot function in the package to just visualize this. We can also predict preferences for the beaches that the users did not respond to. And in a more common application, it would be you have the user has seen just a few products, and you want to know which new products to recommend. And then you use all the data to try to predict, what's the probability that this item is among the top 3, for example. And the color scale shows the probability here. So you get probabilistic recommendations on new preferences for each user. There's a lot of more applications and methodology in this. Just to point out a few, in the BayesMallows package paper, which is soon appearing in the R journal, we have a lot of use cases and tutorials. There is a paper on clicking data, which is published in Knowledge-Based Systems. And we also have an application in musicology that uses this rank model to evaluate how good people are at distinguishing sounds made by humans and sounds made by something like by a computer. So that was a little introduction to the BayesMallows package. Thank you all for listening, and the slides will also be posted at my homepage after this speech. Thank you.
Thank you, Øystein, for the very nice presentation. And okay, so we are apparently having some problems with the fifth speaker. So let's see if actually everything works. So please, Stefan, try to connect and try to have a, okay.
Hello, can you hear me?
Yes, we can.
That's great.
Fantastic. Yeah. Perfect, perfect. So please start sharing your slides and so we can, you can start your presentation.
Yes. Oh, one moment, please. Start the slides.
Yeah.
Sorry. Sorry. Do you see my screen now?
Not yet.
Okay. But I tried. Oh shit. Something went wrong. I got the message. Sorry.
Okay. So can probably wait for a bit until Stefan comes up with or tries to sort out his problems. Otherwise, okay.
Sorry, I try again.
Yeah.
I don't know. See now? Can you see
nothing?
now?
No, apparently nothing is coming up. No. So the, let's say, Emanuela said.
Oh no, again error. Okay, maybe.
No, yeah.
I will try with Chrome. I don't know.
Yeah, we can start the Q&A and then when you come back, you can have your presentation if you are okay.
Yeah.
Okay.
Yeah. Okay. Sorry.
No problem. So I invite all the speakers back on stage so we can have our panel discussion session. So here we are. Hi, welcome back. So hi. Okay. Yeah. Now it's the all of us. Yeah, it's the all of us. So let's start with our questions. Apparently we have quite a lot of them. So let's start with Florian, who was the first. There's a question by Øystein Sørensen. So yeah, an inside job. Okay, so does it use the coordinate descent algorithm to compute the elastic net, or is something else needed with such big data?
Yeah, so it uses a cyclical coordinate descent, so simple lasso implementation, or elastic net if you use elastic net. But the thing is that you need to do this coordinate descent only on a subset of the data because I'm using these strong rules. It's basically statistic that you can compute that would say if a variable will enter the model or not. So you can know in advance that lots of variables will never enter the model, and then you don't need to do the coordinate descent on them, basically. Yeah.
But so if I'm allowed to just follow up, so
yeah, of course.
Is it Friedman et al. Or something? The paper on the elastic net for the lasso. I think they use this active set strategy, right? Where they just use the non-zero variables very long, and then they check every now and then if some of the zero variables should go into the set.
Yeah.
Is that similar to what you do, or do you just like do this a priori and just remove the variables that will never go into the set?
No, it's the same. It's the sequential strong rules. Yeah.
Thank you.
It's a Chip Weber from 2012, I think.
Yeah.
Okay, let's move on to a question for Krystian. Let's say there's Malco is asking you some literature about the topic.
Yeah,
Okay, yeah.
I already answered to this question, but forgot to send the articles about the core parts used in the approach. So I will send it in a minute after
No,
the
yeah,
Q&A.
perfect. So actually, there's another one by Gies van Kessel. So nice presentation. That this method work with models having significant interactions and or nonlinear effects?
Yeah. So in the case of PDP usage as a marginal response, it would rather fail because of the specific how it's constructed, especially because of this aggregation of ICE curves. You may lose because of the interactions, you may lose the information that this marginal response provides, especially if you have two groups of ICE curves that are of opposite trends. But you can force the problem to use accumulated local effects plots instead of partial dependence plots. This is also offered by xspliner, and in this case the interaction this copes better with when the interactions occur. There was also another question about nonlinear effects. Yeah, the answer is the same. Yeah, so you should use ALE plots.
Okay, perfect. So let's move on to. Sorry. I'm trying to use Slack for the questions, but okay. So let's move on to a question for Mustafa. So actually, it's more of a comment. So Fisher is not in the trend these days. Good to see that there are alternatives. So it's nice. I actually have a question. Let's say I did some work in the F-test or variations for the F-tests where you don't respect the assumptions usually made for ANOVA. What do you think about permutational approaches in the field of ANOVA testing where the assumptions are not respected?
Thank you, Matteo. I want to start with Dimitros's comments. Yes, he's right. Fisher is not trending nowadays, but I used just for reference test it in my theoretical part of my presentation. Also, he can see the other alternatives in our package. And after this, your question is, yes, I think the permutational test is more powerful nowadays than the classical methods. And also, I prefer, I advise to use in the violation of assumptions. My favorite test is parametric bootstrap. It is based on bootstrap samples, and it gives really powerful results instead of the classical alternatives. Thank you.
Okay. Thank you, Mustafa, for the answer. So we try again with Stefan presentation. Let's see if everything works. So I ask you all to go away, and let's try Stefan presentation again. Hi, Stefan.
Oh no! Again, this error. Can you hear me?
Yeah. We can hear you.
But now I try again. Just
Okay, yeah, we can see see the screen now.
Great.
Perfect.
Yeah, with Chrome it worked now. Okay. So thank you. Can I start or?
Yeah, of course you can start.
Okay, sorry for the technical difficulties. My name is Stefan Lenz, and I want to present you now our new package, JuliaConnectoR. I want to show you how you can use it to bring flexible deep learning from Julia to R. Why would you use R? You can use R to speed up time-critical portions of your code. Because why would you use Julia? Sorry, because you can use Julia to speed up time-critical portions of your code, because it is fast, and you can also gradually optimize your Julia code without transitioning to a low-level language such as C, but still get a comparable performance. Julia also offers the possibility for differential programming, which means to compute gradients from code, which is useful for new types of AI algorithms. This is, for example, used in the deep learning package Flux, which I will use in the following as an example how you can use the JuliaConnectoR with R and Julia. So, for example, if you want to do this in Julia, you want to create a small neural network. Here, as an example, with 2 layers, you can use the dense function in Flux to create a densely connected neural network layer, and you pass the number of nodes in this function and also an activation function as an argument. Here in this example, we have rectified linear units. Then you can chain this together with the chain function and you get your model. If you would like to do the same in R, you can use the JuliaConnectoR and the Julia import function, which does not know anything about the Flux package itself, but it scans any package that is given and returns an environment that contains everything that is that in this package can act as a function and returns it to R. So all these functions can then be used. They can be called in R and they can also be passed as an argument, as you can see with the ReLU activation function here. Then the result can be also stored in an R variable again. So as you can see, this allows a very tight integration of the 2 languages. If you want to couple your code a little bit more loosely, you can also do it another way. So for example, you can use the Julia eval function. This accepts an arbitrary Julia code that is passed as a string, evaluates it in Julia, and returns the result to R. So here, for example, we define a training function, and in Julia, which is then available in Julia, and it is also returned to R, and you get a function in R as a result that you then can use in R and call with the model and some data to train your model. So what you have seen now is mostly the importing of packages or as a feature, but there are many more features of the JuliaConnectoR which I can't go into detail here because of the lack of time. So what you can see here is a comparison also of the features compared to Julia Call and xrJulia, which are 2 other packages that also aim at connecting Julia and R. And I just want to quickly highlight a little bit of the features we have here. So we put some emphasis on good documentation, and also we have a clearly specification of all these translation that happens, which is important because Julia is a little bit more type sensitive than R. So this is also important to know everything. And then we have callbacks, also the probability. So you can also call back from Julia to R again. And we have special features for convenient interactive use, especially to show the standard output and standard error output, which is especially useful for warning and info messages. And it is also possible to interrupt your code, which is especially useful if in deep learning, where model training can take some time, or you might want to reconfigure your parameters. And there's also some possibilities for data handling. So missing values and data frames are also properly handled between Julia and R. So if you want to know more details, you can check out our article, which is available in arXiv. This also includes an example by using neural ordinary differential equation with time series data. So if you have become interested, you might want to check it out. It's available on GitHub, and you can take a look at the article. And of course, you might want to install it. It's available from CRAN. So thanks for the attention.
Thank you. Thank you, Stefan, for the nice presentation. Finally, we managed to do it. And so I invite all the other speakers on the stage, so we can go on with our Q&A session. So I think now it's time for a question to Øystein. Okay, let me see. So let's start with a question by Fraser. So a really great talk. How well does BayesMallows perform with ranking preferences for new customers? So little to no observed transactions. Okay, yeah, we can.
Yeah, shall I answer that? Yeah. So, I mean, of course, it depends. There has to be some new observations, because, I mean, what you otherwise would probably do is that you have this modal ranking. So if you, for example, have a customer segment that is fairly homogeneous, you would probably recommend to the new customer based on your mean, like the latent variable. And then you would start sort of, the prediction is a kind of imputation, where you impute what the user would, how the user would rank the items or the products that the user hasn't already ranked. And that requires, some observation, because that uses sort of the, algorithmically it compares the patterns in this user to the other users with similar patterns and uses this to fill in. But one of the advantages of this Bayesian approach is that you will always know how uncertain you are. Because if there is too little data, your posterior distributions about this user's preferences will be extremely wide, so that if you look into the posterior distribution, it will tell you that there is a uniform distribution of all possible products, which means you don't know anything. That's your prior. And if you add one data point, then the prior will change, or the posterior will become a little bit different from the prior. And you can see this, and you can follow this to see how much more data you need in order to actually be certain about your predictions. And I think that's one important difference. I mean, it's of course a lot more computationally heavy than collaborative filtering, for example, but in some cases it might be worthwhile because you actually get all this probabilistic information.
Okay, perfect. There's actually, let's say, just a bit of follow-up on this. The person who asked the question asks for if you can give, let's say, a ballpark estimate of a reasonable number of cases after which the prediction starts to be reasonably reliable.
Yeah, I think we've seen in I think the problem is the ratio between like the total number of products and the products that have been ranked. So if you have just say 20 different products, you might get quite reliable estimates, say even after 5 products or ads that have been ranked. Whereas one of my colleagues, or a PhD student at the University of Oslo, she has worked for, I think it's called classified ads, the online ads where you have anything from real estate to people buying, people selling some secondhand stuff they want to get rid of. And they looked at click rates on this. And then you need like, if you have 1 million different ads, you need maybe at least 1,000 clicks or observations on what this user was interested in. So it depends very much on this ratio. So the bigger your universe is, the more data you also need in order to make inferences.
No, yeah, of course. So thank you for your answers. So there are some questions for Stefan. So how performant, how fast is sending data to the JuliaConnectoR via TCP? What about the comparison with the other connectors?
Okay, so xrJulia also uses this TCP connection. So I didn't check especially for this. The Julia call is really more tightly integrated. It's integrated on the C level, so it is, if you have many transition between Julia and R, this will be faster. In our experience, for example, for the deep learning use case, I think it's not so relevant. So you can even do thousands of epochs and communicate between Julia and R. It is no problem. This will result in no noticeable delay. The delay is as much as if you would print something on the command line between these epochs, for example. Yeah. So you can say it is as much delay as you would have if you print some info output between this what's happening here.
Okay, thank you for your answer. So let's start back with Florian. Okay, do you have already implemented other penalization algorithms? Claudia asks, especially for graphical models.
I'm not sure about that. The package bigstatsr is really for dense matrices basically. So it's the data I use in my research. So it's mainly designed for that. So dense matrices. So I'm not sure graphical stuff are implemented right now.
I see. Okay. What about, for instance, mixed effect models? I mean, I'm asking this, and I'm asking this with this question, so it's inside the question list, because I have a similar problem for an application in energy prediction, and I have a terabyte of data, and of course I can store it in memory. So if you can help me with that, I would be very, very grateful.
Yeah, so the implementation relies a lot on these strong rules to discard a lot of variables beforehand, right? And I'm not sure we can derive these strong rules for mixed models.
Okay.
But if you want, just to store the data on disk here, you can still use the formats that provide in this package. And then the accessors, like both in R and C++, are like just matrix accessor. So you can easily implement your own algorithm for this data format.
Okay, thank you very much for your answers. So let's let's move again to Krystian. So there's a question by Alexander Schmidt. Does it make sense to use the generated splines model to create a more robust model? And if so, can the xspliner package export the spline model?
In general, we observed that when the original model was pre-trained, then the spline model performed better. But this is quite expected behavior. So there were the situations when the original model performed very well and was not pre-trained, but the final splines model was very comparable to it. So xspliner provides multiple tools to compare them, and you can then make the decision. About exporting the spline model, I'm not exactly sure what's this about, but you can work with such model as the usual GLM model that you create in R. If you're interested in the exactly splines approximations that it forms, the final model also provides such information, and xspliner provides the functions to extract it and use. Especially I use this in this Shiny application. So.
Okay, I see. Thank you for your answer. So another question for Øystein. Do you have examples of your package with applications in marketing, so digital attribution, CRM recommendations, and so on?
Yes, we have a PhD student who worked in collaboration with the industry in digital advertisement who compared this package or this method to what they already used. I think I don't really know this field, but I think they used collaborative. I mean, I implemented the package, but I don't know like, the other.
No, I see. Makes sense.
Stuff and all the recommender systems that are going on, but I think what they saw is that collaborative filtering, for example, was what you would normally use, because usually they gave just the same stuff. But there were some cases where, like some important edge cases with the outliers, for example, different types of users, where the Bayesian approach was much better at capturing that this user is different from the others, it should have different predictions and so on, so it could improve on that. So that has been used, it's been used there. And I think it actually like has been used in practice there to recommend ads based on what the user has clicked on before. That's the closest I can think of.
Okay, perfect. So thank you very much. There's actually a question by you to Stefan, and a question I share because yeah, the matter has come up with colleagues and colleagues from other fields quite several times. So Stefan, can you comment on how complete Julia is for doing statistics? So can I, example, use it for fitting mixed models or general additive models when R becomes too slow? So if I can follow up on this, why using Julia when you have R, and is it Julia better than R or whatever?
So I personally also use R, and what I like about R is that it just offers so many packages that just work. And in Julia, there's still much work in progress. But for example, where you really don't have what we really don't have in R, and which is simply because of the speed not possible to implement, is this deep learning, for example, or really computation heavy stuff. So there's also, I personally came across some, I don't know, when I was really trying to handle some big matrices, doing some computations on that. So something I want to write myself more or less. So when I don't go to a package, then I just can optimize my code, and this is I have possibilities to optimize this that I just don't have in R, because you can't, for example, reuse matrix code, reuse matrix space in R. So if you want to have, if you have some R code and you say, okay, I just can't do this, I can't just run this in R, this is too slow, then it is maybe it's a good example to write this function simply in Julia and then call it in R. But of course, for example, the plotting is also good in R. So I also think this is a valuable tool, this JuliaConnectoR, because you can still have all the good things from R and add to it, if you need it, the speed of Julia, or also some features. I also heard about optimization, that there are some packages that are new in Julia and that are better than in R. But still, of course, the number of packages and also for the standard statistical methods, you probably are at the moment, if you just want to use it, better off in R. But there are definitely use cases where you can profit from the speed of Julia and also from some new features.
Thank you.
So you basically suggest, if I get you correctly, to use R as some kind of fast prototyping tool, and then actually write fast code and production, it's a production level code in Julia. I don't know if I misunderstood you, but that was the message I took home.
And I've been using RCPP a lot to bind C++ code into R, and maybe Julia would be a good alternative to.
Yeah, I mean, writing C++ code is a pain in the ass.
Mm-hmm.
So if you have, let's say, a better working alternative, and Julia is fast enough, that would be amazing. That would be great. So
Exactly.
Thank you for the presentation, and thank you for the. I mean, it's a very new perspective. I wasn't expecting it. So we probably have a time for a very quick question. So let's see. Okay, so a question for Florian, who's asking, or there's Mohammed Fayas, who is asking for what about Bayesian estimates for splines in this package?
Yeah, I think I've answered in the chat.
Yeah.
Question.
Okay. Okay. So we are just in time. So I would like to thank all the speakers for being here, for the very nice presentation, and for the very interesting Q&A session. So thank you, and thank you also from the organizing committee. It has been tough, but we managed to do it, and I hope you enjoyed it. And I mean, it was a good. I hope this was a good experience for you. So thank you all for this. So thanks.
Yeah, thank you.
Thank you so much.
Bye.
Right.
Bye.